Using the incredible power of the James Webb Space Telescope, researchers at the University of Missouri peered deep into the cosmos and stumbled upon something surprising. 300 objects far brighter than expected. These have been labeled candidate galaxies, potential galaxies existing at the very edge of time. If confirmed, these objects could upend our understanding of how and when galaxies formed in the early universe. What's more, they appear to have existed when the universe was only a few 100 million years old, an era when, according to the standard model of cosmology, the first stars and galaxies were just beginning to emerge. To identify these 300 early galaxy candidates, scientists employed the dropout technique, which spots high redshift galaxies by searching for objects that appear in redder wavelengths but disappear in bluer ones. Once these objects were spotted, the next challenge was to determine whether they truly sit at extreme distances, that is, at very high redshifts, farther away than we would normally expect. In the past, astronomers often assumed that such unusually bright objects weren't early galaxies at all, but imposters that mimicked their signatures. The lead scientists behind this discovery warn that even if just a handful of these 300 candidates turn out to be genuine early universe galaxies, it could force a major revision of our models of galaxy formation.
So what exactly are they?
The ultimate test will come from spectroscopy, the most reliable tool in the astronomer's kit. By splitting light into its component wavelengths, like a prism scattering sunlight into a rainbow, scientists can detect the unique spectral fingerprint of each galaxy. This reveals critical information about distance, composition, and age. The stakes are huge. If these really are fully formed galaxies in the infant universe, our understanding of how matter coalesces and structures form may need to be rewritten. If not, then we could be glimpsing an entirely new cosmic phenomenon, one that played a pivotal role in shaping the universe's earliest moments. Until 2022, the farthest galaxy ever observed was GNZ 11, spotted by the Hubble Space Telescope, a milestone in humanity's cosmic reach. Hubble, with its 2.4-meter mirror and remarkable optics, had carried us farther than anyone before, but it had its limits. Then came the James Webb Space Telescope, equipped with a colossal 6.5-meter mirror and designed to detect infrared, the exact wavelength of stretched, ancient light from the earliest galaxies. Webb didn't just pick up where Hubble left off, it shattered the previous records. Early in its mission, Webb identified a galaxy named JWST 14-0, now the most distant confirmed galaxy, with a staggering redshift of 14.32. In simple terms, redshift measures how much a galaxy's light has been stretched by the universe's expansion. The higher the number, the older the light we're seeing. Then came MOMS 14, with a redshift of 14.44, pushing our view even deeper into the universe's infancy. But it wasn't just the distance that amazed astronomers. It was what the galaxy itself looked like. Tiny, barely 500 light-years across. Compare that to the Milky Way's 100,000 light-year span. Yet, astonishingly bright. Galaxies this early are usually faint, nearly invisible against the cosmic backdrop. Not MOMS 14. It's a stellar firestorm, a rapid-fire nursery of newborn stars in the universe's opening chapters. Yet one detail, or rather one glaring absence, made it even stranger. There's no trace of a supermassive black hole. Most galaxies with such furious star formation harbor a massive black hole at their core, thought to steer galaxy evolution, regulating star birth, shaping structure, and driving growth. MOMS 14 appears to defy that pattern entirely, but MOM-Z14 doesn't. The mysteries don't stop there. When astronomers used Webb's spectrograph to analyze the galaxy's light, they found it rich in nitrogen, unusually rich. This chemical fingerprint matches what we see in some of the oldest star clusters orbiting the Milky Way, suggesting that MOM-Z14 is forming stars in extremely dense environments. That's not what we expected. Galaxies this early in the universe were expected to be chemically simple, made mostly of hydrogen and helium. But MOM-Z14 is showing us that several generations of stars had already formed and died before it. This suggests that galaxy evolution may have begun much earlier than we imagined, and it raises a big question. How many more galaxies like MOM-Z14 are out there? Before the James Webb Space Telescope, astronomers assumed galaxies this ancient would be extremely rare. Now, we're finding more than anyone predicted. These luminous, early galaxies, sometimes called tiny red dots, are appearing throughout Webb's surveys. MOM-Z14 might hold the current record, but it may not for long. And that's where it gets thrilling. The more we search, the more we uncover. Every new discovery challenges what we thought we knew. If galaxies like MOM-Z14 were more common, formed stars faster, and were chemically richer than we expected, what else might we be missing? Could this galaxy be pushing the boundaries of our cosmological models? Current theories suggest galaxies this early should be rare, slow-growing, and simple. MOM-Z14 defies all of that. It's fast, bright, and chemically complex. That doesn't mean our models are wrong, just incomplete. MOM-Z14 is a hint that the early universe may have been far more active than we ever imagined. And this is only the beginning. Later this decade, the Nancy Grace Roman Space Telescope will join James Webb in exploring the early universe. Roman will survey far larger regions of sky with stunning detail. Together, these telescopes could reveal hundreds or even thousands of galaxies like MOM-Z14, each one a time capsule from an era we're just starting to grasp. For now, MOM-Z14 stands as a landmark, a faint flicker from an era when the universe was still finding its footing. But the more we explore Webb's observations, the more the cosmos seems to defy expectation. Some scientists, interpreting the data, have even suggested something radical, that our entire universe could exist inside a black hole. Recent research has revealed a puzzling pattern. The majority of galaxies appear to rotate in the same direction. By analyzing the lines formed by the peaks of the galaxy's arms, scientists can determine the direction of their spin. In a truly random universe, galaxy rotations should be roughly evenly split between clockwise and counterclockwise. Yet the data show a strong alignment. The authors of this study argue that this surprising result, at odds with standard cosmological models, might hint that our universe itself resides within a black hole. To grasp this, we need to understand black hole physics. When matter collapses under extreme gravity, it forms an event horizon, a boundary beyond which nothing, not even light, can escape. Anything that crosses a black hole's event horizon is lost forever to an outside observer. But what happens inside remains one of the greatest mysteries of physics. This is where black hole cosmology, or Schwarzschild cosmology, enters the picture. It proposes that our observable universe might actually exist inside a black hole nested within a larger parent universe. Now consider the Big Bang. According to the Standard Model, the universe began as a singularity, a point of infinite density, strikingly similar to the center of a black hole. If our universe is the interior of a black hole formed in a larger cosmos, the Big Bang wasn't an explosion in empty space, it was the moment matter collapsed into a black hole, giving birth to a new universe inside. This idea carries a profound implication. Every black hole in our universe could be a doorway to a baby universe. It might even explain why the fundamental constants of nature seem so finely tuned for life. Black holes that produce stable universes may be more likely to persist and reproduce, passing on conditions that favor stability. Scientists argue that this perspective could shed light on multiple cosmic mysteries, like why black holes possess enormous entropy, a measure that reflects the immense amount of information contained within our universe. Another piece of this cosmic puzzle is torsion. In extended versions of general relativity, like Einstein-Cartan theory, torsion describes a twisting of spacetime caused by the intrinsic spin of particles, which can affect the curvature of the universe itself. Some researchers propose that this twisting could create a repulsive force at extremely high densities, potentially preventing the formation of true singularities. If so, instead of collapsing into an infinitely small point, a black hole might undergo a big bounce, where its core rebounds and expands outward, possibly giving rise to an entirely new universe within. Scientists suggest that this rapid recoil after a big bounce could be what drives the expansion of our universe, the event we now call the Big Bang. Rather than a singularity erupting from nothing, the Big Bang may have been the rebirth of a universe inside the core of a black hole in a parent cosmos. If true, this would transform our understanding of cosmic origins, implying that universes are part of an ongoing, self-replicating cycle, an eternal cosmic family tree. Another fascinating possibility is that the universe might have a preferred axis. Observations of large-scale cosmic structures suggest that galaxies aren't distributed or moving entirely at random. There seems to be a subtle alignment. This phenomenon, known as cosmic anisotropy, challenges the long-standing cosmological principle, which assumes that the universe is isotropic and homogeneous on the largest scales. If a preferred direction exists, it could hint at unknown physics, possibly tied to the idea of our universe forming inside a black hole, or to deeper interactions between fundamental forces across cosmic scales. Adding to the mystery, the presence of ancient, massive galaxies so soon after the Big Bang strains our current models of cosmic evolution. Yet while the black hole universe hypothesis is captivating, there may be simpler explanations for these anomalies. Some earlier measurements, such as the rotation speed of the Milky Way, might simply be off, leaving room for more conventional interpretations of the data. Either way, the universe is proving to be far stranger than we ever imagined. These unexpected patterns in galactic rotations are sure to push astrophysicists to rethink some of our most basic assumptions about how the cosmos works. What do you think? Drop your thoughts in the comments below. And as always, don't forget to subscribe, because this is your space.